All right. Hello, everyone. Welcome to tonight's keynote session. My name's Travis Humble. I'm from Oak Ridge National Laboratory, and I'll be your moderator for the session tonight. Our keynote session tonight is actually a very special one. We have not one, but two keynote speakers, so it's a double feature. The topic tonight, controlling 1,000 qubits scaling to usefulness without compromising. It's a very provocative title, very exciting topic to think about, because how can we push that boundary for the number of qubits that we actually have control over? Let me start off by introducing our speakers. First is Itamar Sivan, CEO of Quantum Machines. He's the co-founder as well. A well-known entrepreneur. He has a PhD in quantum electronics and microfabrication from the Weizmann Institute of Science. He's received the John F. Kennedy Prize for Academic Excellence in 2015. He was also the ex-managing director of the Weizmann Institute's entrepreneurship program. No surprise here to see a company coming out of such excellent background. And he's played a pivotal role in this through this position and helping to create a culture of innovation and driving forward the growth of successful startups in the quantum computing space. So he'll be one of our speakers tonight. The second, Yonatan Cohen, is the Chief Technology Officer of Quantum Machines, also the co-founder, a physicist and entrepreneur by training. He got his PhD at the Weizmann Institute of Science, focusing on quantum electronics, superconducting and semiconducting devices, as well as microfabrication. Also with a background in the Weizmann Institute entrepreneurship program, he too, working with Itamar, have played a pivotal role in making Quantum Machines one of those leading startups that demonstrate the type of innovation and creativity that we need in order to push the field forward. So they'll be introducing this topic to us tonight. We are expecting about 50 to 60 minutes of the presentation, followed by a question and answer period. When we get to the question and answer period, we do have a microphone located up here in the front of the stage. Come up, ask your question to our speakers, and then we will go through the Q&A process. With that, it's my pleasure and honor to invite our first of the two speakers up, Yonatan.
All right, thanks. Okay, controlling 1,000 qubits. It's quite remarkable that these days in the quantum computing community, we can talk about this no longer as a distant dream, but actually as a practical, concrete goal for the field, with a practical and concrete work plan behind this goal. And it's quite interesting that it's actually happening across the board in the field. So many different players across many different qubit types are actually defining this goal of building 1,000 qubit machine, or around this scale of a quantum computer, at the same time as defining this as one of the next big milestones of the field. And so, of course, 1,000 is just a random number. It could have been, 1,152. But I believe that this number, this kind of scale, really captures very well the essence, the underlying reason that is really the reason why many of us started in quantum computing to begin with. This dream of building a machine that has this ginormous or unbelievable or ungraspable, if that's a word in English, number of the degrees of freedom, essentially 2 to the 1,000 degrees of freedom. This dream of building such a machine where we can actually coherently control the dynamics of such a ginormous Hilbert space to perform useful computation tasks. This is just mind-blowing, and I think it's really the underlying reason why many that kind of reunites many of us in the field. So we can now set this as a real practical goal, which is great. But it's not enough to just build a 1,000 qubit machine, a machine with 1,000 qubits. Really, in order to take advantage of the entire quantumness of this 1,000 qubit machine, we need to build it in such a way that does not compromise on the performance, actually improves performance and squeezes all of the quantumness from the qubits. And while the progress in the field has been quite amazing in recent years, with more and more qubits in a single quantum processor, actually approaching 1,000 already, and with higher and higher quantum volumes and more money also invested in the field, still this prospect of really harvesting the entire quantum or Hilbert space of a 1,000 qubit machine is a very challenging task. And in fact, the road to get there is quite long and full of challenging obstacles along the way. So today we want to tell you a little bit about how do we at Quantum Machines see some of these challenges to reach such a 1,000 qubit machine, and what is the path that we see to overcome some of these challenges, and focusing in particular on the classical electronics control system. This is what we are at Quantum Machines develop. So there are challenges across the entire quantum computing stack, from the quantum processor through the control hardware, the classical control hardware, which is what's responsible to orchestrate and generate the signals, the analog signals that drive the quantum processing unit, and also measuring the quantum processing unit, and also integrating classical processing engines very tightly with the quantum processor, through the control software layer, which is responsible to implement in software the calibrations, the compilations, the optimizations, and eventually the quantum error correction on top of the quantum and classical resources that the QPU and the control hardware provide. And then finally, all the way up to the application layer, where we really need more quantum algorithms that can outperform classical algorithms, and we also need more connection between real-world problems and what can be actually executed, both on near-term quantum hardware, but also on long-term quantum computers. Okay, but to build, and again, harvest the full quantum potential of a 1,000 qubit system, the main challenges, the real bottlenecks still lie in the QPU, in the quantum processor. So really building better qubits with better coherence and better architectures that can allow for more efficient controlling of these qubits. But in recent years, interestingly, not only do we realize more and more what are the bottlenecks also in the control hardware side, we're also seeing that it's possible to sort of offload some of the challenges from the quantum processor to the control hardware layer. And I think this is an important observation because it's sort of it's sort of coming from this realization that really classical electronics is such a much more of a mature technology than the quantum hardware that we have today, that if we could offload some of the challenges from the QPU to the control electronics, then we should do it. Even though sometimes it even doesn't make sense. It sounds like we're putting too much of the challenges on the control electronics, as we will see today. But we can do it. We know how to do it. We know how to build very good classical electronic system. This is perhaps the most mature technology in human history. And until at least we have our perfect qubits or the desirable qubits, then we should try to do it. And I think this realization sort of explains a lot of the, fundamentally explains the requirements that we have on the control layer, the control hardware layer of quantum computers. And so today we have kind of two parts for this talk. The first one, we want to tell you what are the requirements that we see for the control hardware of the stack, according to these different categories that I'll talk about in a minute. And then after that, Itamar is going to come up and talk about what we at Quantum Machines are doing to try to overcome some of these challenges, try to meet the requirements that we're going to talk about. Okay, so we kind of split the key aspects that will allow the control hardware to carry at least some of the burden away from the QPU to four categories. We have scaling, we have analog specs, we have classical processing integration, and we have programming flexibility. So scaling perhaps is the most, sounds like the most trivial one, right? We want to scale our quantum computer, so we need to scale the classical control hardware. And that's true, in fact, and that's, it has some important implications. If you look at a small scale quantum computer, let's say 5-qubit machine, then you will see that actually the controller, the main controller, is a relatively small portion, small part of the system, both in terms of size, in terms of the cost of the system, in terms of the engineering challenge. But if we look at the larger quantum processors that we have today, we're already seeing that the classical controller is starting to become one of the major parts of the system. Again, both in terms of cost, in terms of the size of the system, in terms of the engineering complexity that goes into developing these controllers, and in terms of what limitations it also puts on the entire system, what can be run and can't be run on the system, and so on. So we're seeing this, and it scales with the number of qubits. When we want to grow the quantum computer, we grow the size of the controller. This is not fundamentally a very fundamental requirement. Actually, it stems again from the fact that our qubits are not good enough yet. So we're actually trying to parallelize as much as possible the quantum operations. We're trying to squeeze as many quantum operations to a coherence time, or time that's actually shorter than the coherence time. And that's why we need many channels, control channels that can parallelize the control operations. So if we had perfect qubits, we could actually build a more efficient controller, a simpler controller, for example, using multiplexing as shown here. But unfortunately, this is not the case. So we're going to see some multiplexing probably in the near future in the control layer, but this is just to lower a little bit the number of lines going from the control layer to the QPU, but essentially the scaling is still going to be linear. The scaling of the control system with the number of qubits is going to still be linear in the foreseeable future, and that's an important observation. And this is okay. This is fine. It's hard, but we know how to do it. We know how to build massively scaled up classical electronic systems. And so in the near future, we're already seeing a very dramatic push towards higher and higher densities, meaning the number of channels in a single control rack, and also a push for the total number of control channels that can be synchronized and operate as a single system, can be programmed as a single system, and also a push towards a more economical solutions as we scale up. So price per qubit or price per control channel needs to go down as we scale to massively large numbers of qubits. So that's scaling. The second aspect of the control system that's going to be very important is the analog performance, which is related to scaling, because of course, we need the analog performance of the control system to be to not limit our fidelities, not introduce noise to the system, limit coherence times, and limit gate fidelities. But as we scale up, and again, because we don't have the perfect QPUs yet, the requirements on the analog performance are actually becoming very, very harsh. So some of it, again, is simply because of the fact that we still don't know even how the perfect QPU is going to look like. So you can take a simple architecture like the one shown here with the two transmons and a tunable coupler, and even if you use the same architecture for your QPU, sometimes you want to try to use a certain scheme of gates, like the baseband-based gates, that has certain analog performance requirements that are more important than others, like rise time of the signals or bandwidth or the noise level, the low frequency noise performance of the control system. While on the same system, we can also implement other types of gates, like parametric gates, where other aspects of the control systems are important, like the spectral density or the phase stability. So we're seeing how, again, this level of flexibility that we try to keep in our research and development stage in quantum computing pushes the requirements on the control system. A very good example for this, that even after we choose the gate scheme that we want to work with, we still want a very rich set of gates. We don't want to limit ourselves to the most minimal set of gates that, a universal set of gates, as theory tells us. The ISWAP gate is a very nice example for this. The ISWAP gate allows us to replace a few CZ gates, for instance, or an FSIM gate that can replace even more CZ gates and single qubit operations. So we don't want to just have, a C0 gate or a CZ gate and a few single qubit gates. We want to have a richer gate set so that we can do things more efficiently. So if we do want, for example, an ISWAP, we have new analog performance requirements. In this case, if we're trying to drive couplers parametrically, we have very stringent requirements on the phase stability of the system. Here we have 3 channels. The phase differences between all these channels has to be very stable for very long times in order for the system to perform at the best fidelities. And this actually scales not so nicely because we want to do 2-qubit gates on many pairs of qubits. And so when we scale up the system, it becomes even more complicated. We need to have hundreds or thousands of channels, all phase synchronized with very low drift between these phases. And this puts requirements on the clock distribution of the system, on temperature stabilization, or whether or not we can use certain components, for example, phase locked loop, which cause more fluctuations, more drifts between control channels, and so on. And again, this is fine. This is okay. We know how to do that. People in radar technologies and in 5G technologies have been building phase arrays in the last several years, in the last decade actually, where hundreds of channels have to be phase synchronized very well. So we know how to do it. It's a challenge, but we can do it. And we're going to see these requirements becoming more and more important as we scale up those systems. So that's analog performance. The third category for the requirements on the classical controller is classical processing integration. And this is a topic that at Quantum Machines we view as a very, very important, actually also very, very interesting. It's kind of touching the most intimate, maybe, the kind of very deep interplay between quantum processing and classical processing, how we can offload processing from the QPU to the classical side, to the classical processor, and also what quantum can really, what advantage quantum processing really provides. So at Quantum Machines, we sort of see this quantum classical integration as a key aspect, as sort of this turbo engine that can allow us to move faster towards the future of the field. And we're seeing more and more of the community actually pushing this forward together with us. So nowadays, it's kind of very hot topic of how you can use classical processing and integrate it tightly with quantum processing, what kind of advantage this can provide. So to understand this a little bit better, we first need to define what we mean by quantum classical processing. And according to our definition, you first need to perform some quantum operations in your quantum processor. Then you need to take some quantum measurements and send those measurements to the classical processor, then perform some classical processing on the classical side. And then very importantly, generate new quantum operations based on this classical processing. So we really need to close this entire sort of quantum classical feedback loop to fall under what we call quantum classical processing. And it turns out that many of the sort of hottest topics in quantum computing today do fall under this definition, such as active state preparation, repeatancy success circuits, adaptive quantum error correction schemes, iterative phase estimations, calibration workflows, or running calibrations faster and more frequent, fault-tolerant quantum computing, and variational algorithms. And we took all of these different use cases and we tried to categorize them according to the requirements from the quantum classical integration point of view. And we find sort of 2 dimensions according to which we can categorize the requirements. The first dimension is what is the type of feedback that we need to perform. So whether based on the classical processing, we need to only decide whether or not we play a certain operation to the quantum processor or not, what we call conditional operations, or whether we really want to branch the entire program based on the classical processing, or whether we want to change parameters of the quantum circuit, of the quantum operations based on the classical processing. So these are different types of feedback that are important for different types of use cases. And so this is one dimension, and the other dimension is, of course, the feedback latency requirement. So each one of these different use cases and applications require different types of quantum classical feedback latencies, where we look at the classical feedback latency, which is basically the time from the quantum measurement, including the classical processing, including generating new quantum operations and sending them down back to the QPU. This is the classical feedback latency. And we identified 3 categories for the different requirements for the classical latency. The first category is what we call quantum real-time, or QRT. And that's where we want the feedback latency to be significantly lower than the QPU coherence times, or the times that it takes qubits to change. The typical example for this is active qubit reset, where we measure a qubit, and based on the result, if it's in the ground state, we don't do anything, but if it's in the excited state, we play a pulse to it to put it back in the ground state. Of course, we need the feedback latency from the measurement until the conditional operation to be much smaller than the time that it takes the qubit to change, because otherwise there's no real reason to apply this protocol. So that's quantum real-time. Then we have system real-time, which is where we want the feedback latency, the classical feedback latency, to be much shorter than the time, than the typical time of the drifts in the system. So actually, parameters drift is one of the major bottlenecks in quantum computing today. Systems are drifting, and this causes problems. For example, you can see here in this image, if you track a qubit's frequency, this is the red curve here, it changes with time. Sometimes it actually jumps abruptly, and that's terrible, actually. It's going to hurt your fidelities dramatically if you have such drift and such jumps of the qubit frequency. But if we could actually measure those parameters and correct them on the fly using quantum classical feedback, parametric quantum classical feedback, then we can flatten the curve as shown here. So that's what we call system real time. And the last category is what we call quantum, near quantum real time, or simply near real time, where this is a slightly different category. We don't really strictly require the feedback latency to be lower than something, but we want it to be comparable or lower than the total quantum computation time. And that's simply in order for the classical side of the system to not bottleneck the entire runtime of whatever it is that we're trying to run on the system. Again, this goes back to this idea that we know how to build great classical systems. There is no reason why we should be limited by classical times and not the quantum operation times. This is actually not true for many quantum computers today. In many systems, we spend 99.9% of the time on classical communication between control instruments, on compilation, on classical processing, and not on actually interacting with the quantum device. But this is where we should aim for. So this is near real time. If you want to learn more about this, we actually put it all together in a note that we recently uploaded to archive, where we really talk about these different categories and these different use cases, and give examples from recent publications, recent works, and also unpublished works, and also propose benchmarks for how to evaluate the classical controllers based on these different categories and requirements. And lastly, with regards to this quantum classical integration, again, when we scale up the system, this becomes even harder. The classiest example is quantum error correction, where we make logical qubits from a bunch of physical qubits. And when we run a quantum error correction protocol, we actually need to run a complicated sequence in which we also have a decoder, a classical processor running a decoding algorithm in parallel to the quantum circuit that receives data from the quantum processor, ancilla measurements, and decodes the Pauli frames on the fly. And then at certain points in the algorithm, it needs to also send back feedback to the QPU. And this is a hard classical problem to decode these errors. And in fact, the more qubits we use for a single logical qubit, the harder and harder it gets to implement a classical decoder. So this is really a nice example for this interplay where we can offload from the QPU. You know, we can essentially, in theory, at least lower the errors on the QPU for each logical qubit if we pay with classical overhead. And again, this is okay. We should be able to do it. We can make really great classical processors that can perform these decoding algorithms and integrate them tightly with the classical control system. What we believe we're going to see is a very big push towards systems that are highly programmable, because you want to keep the flexibility. I'm going to talk about it in a minute. But where you have this ultra low latency between the control system and programmable, available, heavier coprocessors such as the GPUs. Okay, so we want to basically connect the GPU to our controller very tightly so that we can run these quantum error correction algorithms and program them from software. Oh, and this actually leads us to this programmability issue, which I think is sometimes overlooked dramatically in the field. You know, we want to implement something, you know, the next milestone of our roadmap, and we just do it. But then cycles times are really limiting the field. So again, because we don't know yet what is the perfect QPU and what are the perfect algorithms we want to implement on them, what is the perfect quantum error correction decoder that we want to use, we need to really put a lot of effort to build platforms that are flexible and that can be programmed from software. So just a couple of examples for this. You know, if you want to implement, for example, this active reset protocol that I just mentioned a couple of minutes ago, you can do it by programming hardware, for example, programming in an FPGA or even creating dedicated chips and ASIC to do something like that. But then tomorrow you go to your favorite theorist and they tell you, okay, why don't we change the protocol? Instead of a conditional based active reset, we perform a repeatedly success based active reset protocol. And there is about 10 different active reset protocols that we can talk about: dynamic thresholding and Bayesian estimation based and others. And then you need to, again, do another cycle of FPGA implementation and testing and so on, and this takes months. Software is different. Software is the shortest times that we can have cycles. So if we can build platforms that give us the kind of quantum classical integrations and latencies that we need, however, they're highly programmable by software, intuitively programmable by software also, because we need to keep the productivity of programming different protocols on the system, then we can actually shorten development cycles quite a bit, and this is, I think, going to be very important going forward. Again, same goes for the decoder. We can build dedicated hardware for decoding. However, we don't know what is the decoder that we want to run. Only in the last several years, there is a bajillion papers on how we can improve decoders. So it's very important that we keep the flexibility and be able to do things from software. Yes, so I think this summarizes nicely the different requirements on the classical control layer. There's, of course, many details around this. And in many cases, we need to bring all of these different requirements together and combine them in various ways that are challenging. But I think it's very important to do it, because the challenge of building better qubit is still the main challenge. And whatever it is that we can do to offload some of the burden away from the QPU towards the control electronics, we need to be able to do it. So with that, I'm going to let Itamar come up to the stage and tell you a little bit about what we at Quantum Machines do to kind of push some of these requirements to new limits. Thank you.
All right. So thank you, Yonatan. Thank you very much. So controlling thousands of qubits, this is what we're here to do. And now we know kind of what are the requirements that we have in order to build the control systems that will allow for this to happen, for this to take place. Now, At Quantum Machines, this is what we're focused on. This is what we do day in, day out for quite a few years now. And in order to explain to you what it is that we do, well, I'm going to do it in 2 steps. And these are 2 steps of 2 paradigms that I believe we have introduced to quantum control, to this field. And the first one that I will introduce is actually an historical one. Okay, so this is like the paradigm that I believe we have introduced in 2019 when we launched our first product to the market. And this is the paradigm that we define as going from what we call a memory-based quantum controller, which is typically called an AWG, arbitrary waveform generator, to what we call a processor-based quantum controller. Okay, so these are 2 different paradigms for doing quantum control, and I will try to explain why this paradigm is so crucial. And I'm going to do this with an example that is very relevant to me, which is basically teaching first graders maths. Okay, so one of my 3 kids is a first grader. We're going through this right now, trying to learn some maths. And there are a couple of ways I would say to teach a first grader math. Okay, not an easy task at all, by the way. The first one is by memory. Okay, so let's say you now want him to know division and multiplication and addition. So one of the ways you can do it is just giving these huge tables and have him memorize it all, right? And actually, it may work. He may actually cross first grade with amazing grades, okay, and be a very happy kid, like the kid that you see on the screen right there, right? But then at some point, he will surely be asked a question, a mathematical question, that maybe is not in the tables that he got, right? So he's going to be terrified, okay? Maybe he will be terrified to the level that he will say, no, I'm not good at maths. This is not for me. I quit. I want to do literature and history. That's great. That's what I want to do, right? And this is perfect. I mean, literature and history is also fine. But maybe if he has the potential, why drop the math so quickly, right? So maybe there's another way, which is maybe the way that I'll try with my son Ari. And this way is to try and teach him to do some processing, right? To process things, not just to memorize things, but actually try to know how the principles go, right? What are the principles? What are the rules? And so on and so forth, right? And maybe if you teach him that well, he will be happy again. But even if he's happy, then maybe he's not yet confident for the future, right? So he's happy now that he can do the things at first grade, but in order to have a real confident kid, like maybe the kid that you're seeing here, you need to decide what is the comprehensive set of mathematics rules and principles that you want to teach him so that he can handle kind of anything that he will encounter along the road. So a real confident first grader is one that can do Bayesian statistics, of course, right? So for sure. All right, so this is exactly what we're talking about here, because a memory-based approach to quantum control is, you can think about it in the following way. If you have a quantum circuit in each and every one of these boxes, right, the gates in the circuit would translate to at least one pulse, maybe many pulses. So you can think about basically generating huge sequences of pulses and loading them to a massive memory in a controller, and then just having the controller spitting them one after the other, right? So typically, as a rule of thumb, if your controller is relying on gigabytes or more of memory, it means that something might be going wrong, right? So actually, in some edge cases, we may need that, and that's perfectly fine. But as a rule of thumb, if you're relying on a huge memory for a quantum controller, something might be wrong there, right? So what we have introduced in 2019 is the quantum orchestration platform, which is, as we call it now, the processor-based approach to quantum control. So the controllers that you're seeing here, this is the OPX. And of course, they have the analog front end in order to control the qubits, measure them, and so on and so forth. This is, as Yonatan said, this is a commodity. We know how to do that. We've done that in other industries already. But the main new thing that we have introduced here is a processor, which is the core of the controller, right? And the processor, which is at the core of the controller, is itself capable of processing and generating all of these pulses while it's running. So as it is playing the pulses and sending them off to the qubits, it is also generating them processing them and processing other things as well. So let us have a look at some of the things that it can do in real time. The different types of real times that Yonatan mentioned earlier. I will also elaborate about that. So what this guy can do, what the PPU can do. So we typically decompose it into 4 elements. The first is waveform generation. Okay, so that means that sometimes you may even be playing 1 million pulses, right? Or more, it doesn't matter. But you do not load 1 million pulses. Maybe you load only 1, right? Or 2, or a finite set. And the system will generate these 1 million pulses or more in real time, right? Based on a specific set of rules that you have defined in advance, right? The other one is waveform acquisition. Of course, you need to be able to get the pulses back from the qubits, digitize them, and plug them into the processor. The third is real-time processing. So real-time processing is actually similar to the example that I gave of the first grader that needs to do processing. And here we're talking about the need or the ability to do comprehensive Turing-complete kind of processing in real time, as tightly combined to the qubits as possible. The fourth component is control flow. So control flow can be the simplest thing, like an if-else statement or a for loop. It can also be a while loop, a switch case, but it can also be any combination of those. So imagine a four cascaded if-else statements within a while, within a switch case. You can find quantum algorithms and quantum circuits that have that, right? So when we're talking about having a controller that we're confident of, like the kid that now know Bayesian statistics, what we need is a controller, and what the paradigm that the OPX introduced is a controller that can actually run any combination of these 4 in real time. So if you look at the space that is spanned by these 4, you actually look at the space of all quantum algorithms and sequences that in principle you can think of. But this is not enough, right? Because there's another aspect. Even if I can run all the most complex sequences I can imagine in real time, still there's another aspect, and that is how easy is it to do so, right? Going to the programming flexibility that Yonatan mentioned, right? Because if I think of an intriguing kind of example, if I give you a silicon wafer, in principle, it can run any classical, any quantum sequence possible, right, from the classical control side. But then you will need to take it to TSMC and fabricate something and then program it and whatnot. But what we're talking about is really being able to run the most advanced quantum sequences, the most complex quantum sequences, process them in real time with very little effort, right? And for that, we have developed Qua, which is an open source programming language, widely used by now by a very large community. And in Qua, you can actually program any sequence that lives in this space that I just presented to you. So things like playing the pulses, measuring the qubits, which are saved to some real-time parameters, like the I that you can see on the right-hand side. Things like processing, comprehensive Turing-complete processing. So here you see an example like A equals I squared, where I was just measured plus square root of cosine of 5, whatever. You can write whatever you like here. And then even having control flow that is based on these measurements. And here you're seeing some advanced examples, not just the active reset, like an if I greater than something, but also you see that here I'm changing the amplitude of a pulse and the duration of a pulse based on something that I just measured, right? This is a very advanced use case that might be needed in very particular quantum algorithms. So if we're talking about having something that is really you can be confident of for the future, it has to be able to run these very complex sequences very easily. And the last is also timing control. I won't elaborate about that too much in this session. So thanks to this new paradigm that we have introduced in 2019, we were able to grow pretty fast, having now more than 250 customers globally and over 150 employees globally, employed in 10 countries. And also seeing the impact in terms of one of the measures, at least in the scientific community, of dozens of high impact publications in high-impact journals published now yearly. Okay, and we see, of course, these numbers go up month over month. So this is a really something that is that we're tracking, and for us is the best measure for the success of the products. So I have here a few examples in which this tight quantum classical integration brings value to customers. And I will use the terminology, at least in part of what that Yonatan mentioned. So the first is quantum real time. So this is some data from the Oscar Painter lab in Caltech, where they could speed up very substantially their quantum experiments once they started introducing active reset for their 10-qubit devices. So this is kind of the first step, the most elementary step that you can get. The other is near real time, as Yonatan introduced. So this is kind of the second tier. This is from Lawrence Livermore, where actually they were able to scan pulse parameters on the fly to reduce experiment runtime. So this is very different from one experiment to the other, but definitely something that can make a big impact in a lab. The third is here what we call system real time. So system real time is, as Yonatan introduced it, it is the time scale of drifts and fluctuations in the system. Okay, so it is not necessarily related to the coherence time of the qubits, but it is some variation in the device that we may want to compensate for. So what you see here is a Rabi chevron measurement was done at UNSW on a spin qubit device. And the interesting thing, you cannot see it from the graph, I will explain it, that is here is that while measuring this graph, actually the gate of the SCT of the device drifted. And while measuring this graph in real time in the pulse processing unit, we actually compensated for it. Okay, and this, you can think of it as both speeding up the experiment, of course. I mean, because you don't have to go back to the computer in order to basically calculate the drift and then compensate for it. But also you can think of it as increasing the quality of the results, right? So this is a very unique example. The next example is taking me back to the first grader. And this is a very recent publication from Ferdinand's lab in the Niels Bohr Institute. Ferdinand is over here. You can go and ask him some questions afterwards. And what you see here is actually that there is a parameter here, the Overhauser gradient between the two dots that form the qubit, which is heavily fluctuating, right? This is, you can see it on the left-hand graph, right? So heavy fluctuation. And what they did in this experiment is they actually evaluated with a Bayesian estimation in real time the value at every point of time, right? And in real time, they compensated for it by changing the duration of one of the pulses over there, right? So basically, I would say this is effectively improving the coherence time of the qubit, right? So it's not just reducing runtime, but it's actually bringing better results with the same device just by running this thing in real time. And believe me, just like it would be hard to teach a first grader Bayesian statistics, it is also hard to run Bayesian estimations in real time on a quantum processor, okay? The next example that I have here, actually, Yonatan already showed it. So this is what we do when there's fluctuations of the frequency of the qubit. So we can compensate for that also in real time, performing a two-point Ramsey in real time, and then changing the frequency in real time. So you can see here, this is easily seen. You see the off and on. So off is if you don't change anything, and on is, of course, if you detect these fluctuations and you compensate for them in real time. So obviously the quality is very different here. And last but not least, because we don't want to talk only about spin qubits and superconducting qubits, where we leverage these real-time capabilities is in the case of neutral atoms, where we use the ability in real time to change pulse parameters in order to arrange the atoms in a 2D array. Right? This is from Mark Sefman's lab, who is also here, performing some really nice results that we got to in only about a couple of days of the installation. The last example that I'm going to give actually in this context is it combines both the real-time capabilities and if you wish, the processing that can be done in real time, but also with the programming flexibility. And this is just a very simple, maybe the simplest bit error correction code one could think of, just kind of to get the idea. So it's a bit flip code. It does include some processing and some feedback in real time. And the idea is that it is all implemented very seamlessly. Oh, this was too quick. No, it's okay. All implemented in Qua very seamlessly and can be run pretty much out of the box. There's nothing hidden here. Everything is based on Qua primitives and can run in real time with very, very low latencies. So this paradigm that we introduced with the OPX in 2019, it covers these three elements that Yonatan talked about: flexibility, classical processing, and analog specifications, right? But obviously there is something that is still missing, and that is the scaling, right? We still need now a system that can scale up to thousands of qubits. And this is what we're here to talk about today. But I do want to say that scaling is not independent of these three. In fact, if you want to be more kind of rigorous about this, scaling means scaling all of these, right? So scaling the flexibility, scaling the classical processing, and scaling the analog specs, because the analog specs also depends on how you do the scale up. So, are you ready? So to tackle the scaling, which is the fourth piece of what Yonatan mentioned, we have introduced OPX 1000. So OPX 1000 is a scaled up controller. It can address 1,000. This is just kind of a number. It can be thousands of qubits. So it has an extremely high density of control and readout channels. So 64 outputs and 16 inputs for a 3U rack unit machine. It has synchronization capabilities over thousands of channels, seamlessly, all-to-all connectivity for data sharing. So this is really going for thousands of channels very, very easily. However, at the same time, it still maintains what we call the OPX-ness. So the seamlessness of running very complex sequences. It has a 16-core pulse processing unit, PPU, with unmatched processing power to be used in real time, and very, very easy programming. The last is state-of-the-art analog specifications, which we find is important for this stage of scaling up. So ultra-low jitter, you can see some of the numbers here. Very high resolution, amplified mode with 5-volt peak-peak, unmatched phase stability in 2 gigasample per second, which again, for some of the platforms is essential. And the last is that it's data center ready, not just in terms of certifications and so on and so forth, but really into its architecture. We have built elements that make it suitable to go into a data center and play a crucial role in building quantum readiness for high performance computing. So we hope that as we have introduced this impactful paradigm in 2019, which captured a lot of traction in this industry and brought a lot of impact, this new paradigm shift will do the same impact. So now we're talking about taking something that was more of a lab controller to something that is much more of a quantum data center infrastructure. And can be scaled up to massive numbers. Other than that, we have many more things that we're doing at Quantum Machines. I'm happy to present anything that you see here later on in the booth or this evening. And with that, I'd like to thank you all for your attention.
Ladies and gentlemen, We're now in the question and answer period. There's a microphone up here. Please feel free to come up and ask questions to either of our speakers. They're happy to take this. I think that this was a pretty exciting and compelling presentation of not just the challenges that exist in the control infrastructure, but also the solutions that you all have put into this. I guess I have to ask you one question. So the OPX 1000 has 64 outputs. That's not 1,000 outputs. Is this because of the way that you're multiplexing the signals together?
Right. So actually, you will need to use many of these in order to get to the thousands. So typically, to get to 1,000 channels, you would need, I believe, 17 OPXs, which are seamlessly synchronized all together. They have all-to-all connectivity in terms of data sharing in real time with ultra low latency. So this is where you get to 1,000. It's extremely high density, even if you have many boxes.
So this transitions us into that quantum datum center paradigm when we're now talking about that much infrastructure to operate these systems.
Exactly.
Great. Questions from the audience? You guys are awful shy tonight. Itamar, can you tell us a little bit more about Qua? Is that as a language, my impression was that it may be something that you would expect the field developer, the electrical engineer to deal with. Is that the right community to target this for?
So can you repeat the question again?
The Qua language,
Yeah.
Who do you consider the target community?
Oh, the
for that
target
language?
community.
Yeah.
So the target community is really the physicists that develop quantum computers or physicists that do experiments in the lab. So this is, Qua is actually the lowest, I would say, abstraction level one could imagine for a quantum computer. So it's like you can think of it as an assembly level code. So typically it would not be used by an end user of a quantum computer or anything like that. So this is very, very low level, as low as it gets for the control. So with the most primitive commands that you can think of, like playing a pulse and measuring a qubit and doing the raw processing needed. And it is comprehensive in the sense that it both has a full set of quantum gates, again, in the pulse level sense. So again, playing a pulse with complete freedom for its shaping. But also it's Turing complete in the classical sense. So you can do any processing in it. And then it also has the interplay. So any quantum command that you would do can be influenced by a classical processing that you wrote, and vice versa. Right? So you can have a classical parameter that is influenced by a quantum measurement. Right? And you can have a quantum gate, so a pulse, that is influenced by a classical processing.
Mm-hmm.
Right? So it's a comprehensive language. So it's a Turing complete on the classical side, but then it's comprehensive also in the quantum classical combination.
So in this sense, learning how to use that language, it sounds like electrical engineers, those with analog signals background, this would be a natural place for them to get engaged.
Yeah, so I think that it's extremely easy to learn for anyone who is familiar with any type of programming.
Mm-hmm.
And I mean, typically within a couple, like, it depends on the person, but between a couple of hours to a couple of days, I mean, people are up to speed with that. And yeah, so. Yeah.
Great. Let's go to our microphone. If you could introduce yourself and ask your question.
Hi, my name is Romy. I'm from the Weizmann Institute. My question is about the noise overhead that might be added by adding many more control units. Is there any additional noise overhead that's added, when trying to diagnose the noise with decoders and correct them? Like, you're adding many more channels. So I'm wondering how that's mitigated or if you've been seeing that as well.
No, I didn't get the question entirely.
Like, is there any noise overhead that's being added
Any
by, how do I say this? By the fact that you're adding a lot more channels,
Yes.
Control units.
Mm-hmm.
So there's more opportunities for noise, I mean.
Yes.
So have you been seeing this, or how is this being mitigated?
So I think that, so this is a great question. So first of all, yes, if you have more channels, basically you could have more noise. it would typically not be in the control boxes, but it can be in the fridge, right? But there's another aspect which Yonatan, I think, kind of very briefly talked about, which is that once you have a very large number of channels, actually the drifts between them can actually grow, right? And this is definitely something that we took care of. And this is what I was kind of referring to when I said that, you know, you do the scaling, but then you need to make sure that the analog specs, they scale together, right? So you definitely need to compensate for anything that comes with scaling in terms of the analog specifications. So this is definitely a very important aspect that is taken care of. Yeah.
Hi, my name is Samudra, and I'm from the University of Tennessee. So my question is, thanks for the great talk, by the way. As you're scaling up to 1,000, you talked about Bayesian estimation methods, and especially, you know, in my experience, those don't scale very well. So especially, you know, when you think of algorithms like Metropolis Hastings and all, you run into just after 10 parameters, it becomes quite, you know, complex. So would those kind of classical processing techniques still be useful when you scale up to, you know, 1,000 qubits?
So that's a great question. Basically, so I would say several things here. So the example that I gave here is an example where you would do the Bayesian estimation for this. This was for a single qubit, right? And in principle, this is scalable in the sense that actually you can do it for many qubits in parallel, right? Because I mean, if you saw the OPX 1000, it has these modules. Each one of these modules has a 16-core post-processing unit. Each one of them can do extremely heavy processing, right? So actually, there's a lot of processing power in this system. So this is definitely scalable, and you can also share some of the processing across these processors. But in terms of if you're doing some Bayesian estimation that would be based on acquiring data from all qubits and then combine them, so I would have to look at the exact. We'd have to be concrete in terms of the example, but it might be that maybe now, you know, you want to do a Bayesian estimation on a too large vector, right? That the probability distribution is too large. So then yes, you would have to go to the next level of processing, right? Maybe to a GPU that's in the vicinity of the controller, right? And this is where, for example, we have with NVIDIA, we have the DGX Quantum, for which we're developing an ultra low latency communication channel between the PPU and the GPU.
Makes sense. Thank you.
Yeah, come on.
Is it working? Okay.
Yeah.
And maybe I can just add to this. The GPU is exactly one of the reasons why we're making this low latency interface to the GPU together with NVIDIA is exactly related to this question. Because yes, if we want to scale up some of these system real-time compensations and also frequent calibrations of the system, then we need heavier classical processing to do that, and we can afford the extra latency that we pay to go to an external GPU. And actually, some of these estimation methods are now these days are being changed also to be based on neural networks. So recent works from Yale, for instance, where you can see how we can use neural networks to optimize waveforms for control. And that's something that can be run very nicely on a GPU in a closed loop with the quantum controller. So.
Quick question on the whole stack up of the array of the equipment. Have you looked at, so different topic, have you looked at what the classical people are doing for machine learning and wafer scale integration of processors? So Cerebras, for example, I forget how many processors they have on a wafer, maybe 4,000. So they use that in the machine learning environment, but I just wonder if there's a solution like that which would fit in here, so you didn't have to have an entire array. You would have essentially a multiprocessor core that was already tied in on a wafer level scale. Those are not analog devices. Those are CMOS, so it's high power. I think it's a couple of megawatts to run one of those things. But I'm just curious if that's another area of thinking in this space to scale up what you're doing.
So yeah, so this is a great question, and this may definitely play a role in the next steps. But the PPUs now are actually implemented on FPGAs, which is the right thing to do at this stage of quantum computing, because you need the flexibility, right? Actually, the FPGA logic can change sometimes, every month, because there's someone who's saying, oh, I need this feature, I need to change this. So it actually changes, but down the line, this may very well be kind of the way to go. Thank you.
I think you just answered my question before I asked it, but basically what I wanted to ask was, what were the computer architecture challenges when you were designing the PPU as compared to like a traditional CPU? But I guess if you're using FPGAs, then were there any specific things you had to change in the traditional computer architecture paradigm to make this happen in like for real-time control?
Yeah, so the architecture is very specific. It is very specific for quantum computing. So basically, if you look at a I don't know, a CPU or a GPU, doesn't have anything to do with naturally anything to do with waveform generation, right? So it is a unique processor, and definitely the challenge is having many things being done in parallel while being synchronized and asynchronized at times, right? So you actually need many cores doing different things, but also within each core, you have processing done, generation, acquisition. You have many things which are being done, and they all have to be synchronized and asynchronized at different times. I think this is one of the biggest challenges in architecting this thing.
I've been Frenzinger, Universal Quantum and University of Sussex. So the talk is all about 1,000 qubits, which is a very interesting number, because it's 1,000 is too many for NISQ and far too little for fault-tolerant operation. So my question really is, how does this scale to numbers, or how do you have an avenue or plan how to scale this from 1,000 to 1 million or 10 million, which is the numbers you'll need for fault-tolerant operation?
So what's shown here today would take you to thousands, okay, depending on the specific architecture of the QPU. Maybe it's 5,000, maybe it's 10,000. But beyond that, we'll have to have another presentation. So of course, some of these elements will remain and will be taken forward, but I mean, some things will have to change. So the boundaries of this conversation is for the thousands, and as Yonatan said, this is like maybe a random number. It could be 800 or 1,300 or 2,500, right? So, but I don't know. Human beings have to have like these some type of quantization. So 1,000 is something that is really easy to grasp, given our numbering system. Yeah.
Hello, my name is Kadir. I am from ETH Zurich, and I am electrical engineer. So you said 1,000, and okay, let's say roughly, and each of your boxes has 64 channels, right? So then, how many of them your boxes are needed then to control this 1,000 qubits? And the second question is that, let's say 60 of them. So then if one researcher wants to make one logical qubit using 1,000 qubits, so then he wants to make this quantum error correction. So he needs to access all this 1,000 qubits quantum states and then run his quantum error correction. Let's say he will use this GPUs. So you said that it is possible to connect your devices to GPUs, but still, do you think that it is easy to do, to transfer all this to the GPU from 60 devices and then make some decision making there and then send again back to all this 60 boxes. So how do you see this scalability in this aspect too?
Yeah, so this was a yes, no question. So the answer is yes, I think it's going to be easy. But so there are two layers to that. So running things across dozens of boxes is easy because there's synchronization between them and there's data sharing between them. And from a programming perspective, there's nothing unique about writing something for 2 boxes or 12 boxes. Right. So when you write code for this platform, I mean, there's nothing different, right? So this is when using these boxes. Then for the communication with the DGX, so yes, this is why the DGX has 2 elements. It has the software element and the hardware element. The hardware element is developing the link, and yes, we're making it pretty easy to feed the data into the GPU through the I won't go into the details now, but through the proprietary connector that we're making for that. But then I do want to say that if you're, I mean, in most use cases, I mean, you will not, if your QPU is now growing, it's not like any computing that you're doing, for example, in the sense of error correction, will now need forever to take the data from all qubits, right? So at the end of the day, it goes until the limit, for example, of a logical qubit, right? So you see what I'm saying? So yeah, I believe this is definitely going to be, I mean, easy, right? I mean, in experimental quantum physics, nothing is really easy, right? But I mean, as easy as it gets, the quantum side will be much harder. Orders of magnitude harder. So at least the classical side is taken care of.
Itamar, if I could follow up on this, if I understood, if I had multiple OPX 1000s, I could actually communicate between them, or at least use them in parallel.
Yeah. I mean, you can do for example, let's say you want to play a pulse from one machine, which has some parameters dependent on a measurement that you did in another machine. So this is as seamless as writing, as you would have written it for a single machine. Yeah.
Okay.
And the data will be transferred. Yeah.
Very interesting. Yeah. Great.
So, Greg Bird, NC State. My background is computer architecture. You seem to have excited the computer architects in the room. So my question is about the memory side of this, and Yonatan mentioned if you're using gigabytes of memory, you're doing the wrong thing. So my question is, what is sort of the memory footprint of one of the boxes, or what's addressable, what's inside the box, what's on the chip? It's just some rough numbers about how the memory architecture looks.
So there are different types of memories. So for example, you have a memory for the instructions, right? Like you have in a normal computer. You have a memory for the waveforms, and then you have some backup memory, either for more waveforms that could be streamed in the course of time, or also streamed for data that would be streamed out, right? So for the things that typically run very much in real time and with ultra low latency, we're talking about, and please, Yonatan, correct me if I'm saying something which is wrong. So we're talking about orders of magnitude. I mean, I don't know the exact number of megabytes, right? For any type of memory. But then still, you do have gigabytes of memory as kind of backup in the box for either streaming more waveforms as needed, and also for data that is being streamed out, right? So for edge cases, you do need more memory.
Okay. And what's your, I mean, the 16 core chip that you have, what's its memory bandwidth, or how does it access memory that's off the chip?
Memory bandwidth?
Yeah, the bandwidth off the chip. How many memory channels and things like, I mean, just curiosity.
No, they just told me to go on the stage. So the way we do it currently is that the waveform memories and the instructions memories are actually implemented in the FPGA.
Great.
So we don't have, so we do have like an extra DDR, but as Itamar said, this is as it's kind of like backup. So we do caching from there, but
okay.
Yeah.
Yeah, great. Thank you.
Itamar, so you gave examples of different technologies that you've been able to interface with. I guess I'm curious, is there one that is the hardest to work with?
The hardest. So I mean,
from a technology level, no personalities needed here, but
yeah. So I mean, I guess there are people working on different platforms in the audience. I don't want to I want to be personal either, but let's talk from, for example, from a latency perspective and how things are stringent from in terms of timing. So I think that, for example, superconducting qubits are the most stringent. So you really need to go in almost anything you do to tens or hundreds of nanoseconds timescales, which is similar also to the spin qubits. But I think these are the most stringent ones that we see in terms of timing.
So it's really this timing issue that kind of leads the list of challenges there.
Yeah, in theory, I mean, if you don't have any timing restrictions, you can do everything on a CPU, right? I mean, it would take forever, but that's okay. But then the thing that is most limiting is the coherence time of the qubits, right? So I mean, the more the shorter their coherence time is, then the faster you need to act, or the shorter their gates is, the harder it is, right? Because you also need to generate these gates. If these gates are very short, then you have a smaller time to prepare them, right? Because you want to prepare them in real time, right? So I would say that these two platforms are harder in this regard.
I guess the slightly related question that came up earlier in terms of the engineering and these types of issues is the power consumption. Do you, and I know you mentioned that, and I think I value this, is the ability to prototype and rapidly evolve and using FPGAs and these types of approaches, it seems like gives you a lot of flexibility, but they're probably more power hungry than, you know, what it may eventually look like. Do you have concerns on the power side for the scaling at this stage?
So for any request that we got so far from, I mean, we provide our systems to those who build quantum computers, right? So any request that we got from now, we could address it, right? So, I mean, this is the concern of our customers. So for now, we're not concerned. But again, going kind of to the question, one of the questions of what's going to be afterwards. So afterwards, actually, there's still open questions, right? How are we going to scale this further while being also energy efficient and so on and so forth?
Okay, great. Any more questions for our speakers tonight? Okay, with that, let's close the session. Give a big round of applause for both of our speakers. Thank you, Itamar. Thank you, everybody. That closes our session for tonight. We'll see you bright and early tomorrow morning for our next keynote talk. Thank you.